Having the sun as your neighbor is hard. The heat is brutal. The radiation is relentless. There is no thick sky, no oceans, no clouds to soften the sunlight. During the long Mercurian day, the surface heats up to about 430 degrees Celsius, hot enough to melt lead. At night, with almost no atmosphere to hold that heat in, temperatures fall to around minus 173 degrees. A swing so extreme it feels hostile to anything that tries to last. By every simple rule, this world should be dead. So why isn't it? We've only visited Mercury with 2 missions in all of human history, Mariner 10 and Messenger, and now a third, Bepi Colombo, is on its way, taking a long, careful route just to survive the sun's gravity. Tonight, we're going to listen to Mercury's story. Quiet on the surface, but pushed to the limit, and still full of secrets. Mercury sits closer to the sun than any other planet in the solar system. On average, just 0.39 astronomical units away, less than half the distance between Earth and the sun. From that position alone, it receives several times more solar energy than Earth ever does. Sunlight there is stronger, more concentrated, and far less forgiving. And yet, Mercury's extreme temperatures are not caused simply by being too close. They are caused by something else. Mercury has almost no atmosphere. There is no thick blanket of gas above the surface, no clouds to scatter sunlight, no air to trap warmth once the sun goes down. On Earth, our atmosphere works like insulation. It absorbs heat during the day and releases it slowly at night. That balance is why our temperatures remain relatively stable. Mercury has no such system. This creates one of the most extreme temperature swings in the entire solar system. Not because Mercury is always hot, but because it cannot hold heat at all. It is important to pause here and correct a common misunderstanding. Despite being closest to the sun, Mercury is not the hottest planet. That title belongs to Venus. Venus is wrapped in a dense atmosphere rich in carbon dioxide. Its clouds trap heat so efficiently that surface temperatures remain above 460 degrees Celsius day and night, everywhere on the planet. Mercury, by contrast, heats and cools freely. It absorbs sunlight quickly and loses it just as fast. In many ways, Mercury behaves less like a planet with weather and more like bare rock exposed directly to space. Imagine placing a stone in a fire, then pulling it out and dropping it into ice. The stone itself does not regulate temperature. It simply responds to its environment. That is Mercury, a world without moderation, without buffering, without protection. And yet, this brutal simplicity creates something unexpected. Because heat escapes so efficiently, some places on Mercury never warm up at all. Near the planet's poles, the sun sits low on the horizon. Inside deep impact craters, sunlight never reaches the bottom. Those regions remain permanently dark, permanently cold. Cold enough that ice can survive there for billions of years. And yet, in the coldest shadows of this scorched world, something impossible remains. Mercury spins in a very specific way. Its axis is almost perfectly upright, with barely any tilt at all. That small detail quietly reshapes the planet. Near Mercury's poles, the sun never climbs high in the sky. Its light skims the horizon, never reaching deep into some impact craters. Those places have remained in darkness for billions of years. Permanent shadow. Inside these craters, temperatures never rise. They stay locked far below freezing, untouched by the sun's heat. For a long time, scientists suspected something unusual might be hiding there. Radar signals sent from Earth reflected back in a strange way. Too bright, too consistent. The pattern looked familiar. It looked like ice. The idea seemed impossible at first. Ice on the planet closest to the sun. But suspicion became evidence when the Messenger spacecraft entered orbit around Mercury. From above, it measured subtle changes in surface chemistry and neutron emissions. Those measurements told a clear story. At the bottoms of these permanently shadowed craters, there is water ice, not a thin coating, not something temporary, but thick deposits, buried beneath a shallow layer of darker material, protected from direct sunlight. The ice did not form there. It arrived later. Over billions of years, comets and water-rich asteroids struck Mercury's surface, delivering small amounts of ice each time. Almost everywhere else, that ice disappeared quickly, baked away by the sun. Here, it stayed. Temperatures in these shadows remain low enough, sometimes below -170 degrees Celsius, to preserve ice for immense spans of time, longer than the age of complex life on Earth. This discovery quietly changed how scientists think about Mercury. Because ice is a volatile substance, it does not survive easily, especially not on a world so close to the sun. And yet, Mercury preserved it. Not through thick air, not through weather or clouds, but through geometry and stillness. In that sense, Mercury is not simply extreme, it is precise. It shows that habitability, in its broadest meaning, is not only about warmth or comfort, it is about stability, about places where conditions remain unchanged, long enough for something fragile to last. NASP, under the sun's constant pressure, it is slowly losing itself, one atom at a time. Mercury does not have a true atmosphere. There is no thick layer of gas wrapped around the planet. No pressure, no weather. Instead, Mercury has something far thinner, an exosphere. It is so sparse that its particles rarely collide with one another. Individual atoms move freely, rising from the surface and drifting back down, one by one. This exosphere is made of only a few elements, mostly sodium, some potassium, traces of hydrogen. They do not stay there for long. Every day, Mercury is exposed directly to the sun. Solar wind streams past the planet, carrying charged particles at enormous speeds. Micrometeoroids, tiny grains of dust, strike the surface again and again. Each impact, each collision, does something subtle. It knocks atoms loose. Sodium atoms are lifted from the ground and released into space. Not violently, not all at once. Quietly. Then sunlight does something unexpected. Light does not only illuminate, it exerts pressure. Photons strike sodium atoms and push them away from the sun, gently but continuously. Over time, this steady pressure sweeps the atoms into a long, trailing stream. The result is something extraordinary. Mercury grows a tail, an invisible tail stretching up to 5 million kilometers into space, many times farther than the distance between Earth and the Moon. It is not a comet's tail. There is no ice vaporizing, no dramatic plume. This tail is thin, ghostly, a metallic shadow shaped entirely by sunlight. And the process never stops. Day after day, Mercury loses tiny amounts of itself. Atoms lifted, carried away, gone. The loss is small, measured in grams, not mountains. But over immense spans of time, it adds up. Mercury is not crumbling. It is not breaking apart. It is being eroded gently and continuously by the star it orbits. And to understand why Mercury looks the way it does today, we need to look not just at what it is losing, but at the scars it has already endured. Mercury does not experience time the way we do. Not because clocks would run differently there, but because motion itself follows unfamiliar rules. Mercury's orbit around the Sun is highly elongated. It is not a neat circle. It stretches outward, then dives inward again. At its closest point, Mercury is pulled deep into the Sun's gravity. At its farthest, it briefly escapes that grip. The distance between those two extremes changes dramatically over every orbit. One full trip around the Sun takes just 88 Earth days, less than 3 months. But Mercury is not tidally locked. It does not keep the same face turned toward the Sun the way the Moon does toward Earth. Instead, Mercury spins in a rare and delicate rhythm, a 3-to-2 spin-orbit resonance. For every 2 trips Mercury makes around the Sun, it completes exactly 3 rotations on its axis. This balance is stable, precise, and deeply unintuitive. Because of this resonance, a strange thing happens on Mercury's surface. If you stood on the ground and watched the Sun, a single sunrise would take an incredibly long time to return. One full solar day, from sunrise to sunrise, lasts 2 Mercury years. That is 176 Earth days, nearly half an Earth year of daylight, followed by nearly half a year of night. Heat does not arrive briefly and move on. It lingers. The Sun rises slowly, climbs the sky, and stays there, pressing down for weeks at a time. And near Mercury's closest approach to the Sun, something even stranger occurs. The planet's orbital speed increases. Its rotation cannot keep up. For a short period, the Sun appears to slow, then stop, and briefly move backward across the sky. It is not an illusion. It is geometry. Then, gradually, the Sun resumes its forward motion, and the long day continues. This distorted sense of time reshapes everything. Surface materials heat longer, cool longer, expand and contract more intensely. The extreme temperatures Mercury experiences are not only a result of distance, they are a result of exposure. Too much sunlight for too long without relief. On Earth, the cycle of day and night protects us. Heat builds, then releases. The rhythm stays gentle. On Mercury, the rhythm stretches. Time itself becomes an environmental force. And when time behaves this way, when heat and darkness linger far beyond what rock is designed to endure, the surface does not remain unchanged. Stress builds slowly, silently, and when it finally releases, it leaves marks that last forever. Because on Mercury, every moment lasts longer, and every impact matters more. At first glance, Mercury should be easy to reach. It is the closest planet to the Sun, closer than Venus, closer than Earth. So the intuition feels simple. If we can send spacecraft to Jupiter and Saturn, surely we can reach a planet that close. But space does not work on intuition. Going outward in the solar system is surprisingly forgiving. When a spacecraft travels toward Jupiter or Saturn, it climbs away from the Sun's gravity. It slows down naturally. And when it arrives, the massive gravity of those planets can help it break and settle into orbit. Mercury offers no such kindness. To reach Mercury, a spacecraft must fall deep into the Sun's gravity well. As it moves inward, it accelerates rapidly, faster and faster. By the time it crosses Mercury's orbit, it is moving far too fast to stay. To orbit Mercury, a spacecraft must lose an enormous amount of energy. Not because Mercury is massive, but because the Sun is. In this region of space, the Sun acts like a cosmic accelerator. Everything that approaches it is pulled forward, stretched, and sped up. Slowing down near Mercury is harder than speeding up toward Jupiter. There is no easy braking system, no large planet nearby to steal momentum, no single maneuver that solves the problem. Instead, spacecraft must take long indirect paths. They loop around the Sun. They pass by Earth, Venus, and Mercury itself multiple times. Each flyby steals a small amount of energy, step by step. It is a slow process, measured not in months, but in years. This is why Mercury was ignored for so long, not because it was uninteresting, but because it was dynamically expensive. The challenge is not heat, it is not radiation, it is motion. Fighting the Sun's gravity requires patience, precision, and risk. Every successful orbit around Mercury represents thousands of careful calculations and a willingness to arrive slowly on the Sun's terms. This difficulty gives weight to every piece of data we have. Every measurement, every image, every discovery. What we know about Mercury was not gathered easily. It was earned, and only a few missions have ever dared to fight that battle. For most of human history, Mercury was only a point of light, visible at dawn or just after sunset, always close to the Sun, always difficult to see clearly. That began to change in the early 1970s. In 1973, a small spacecraft was launched on a long, careful journey inward. Its name was Mariner 10. At the time, reaching Mercury directly was impossible. There was no fuel powerful enough to slow a spacecraft down once it fell toward the Sun. So engineers tried something new. They used Venus. Mariner 10 passed close to Venus and borrowed a little of its motion. That gravity assist bent the spacecraft's path inward, not straight toward Mercury, but into a looping trajectory that would cross Mercury's orbit again and again. Between 1974 and 1975, Mariner 10 flew past Mercury 3 times. It never entered orbit. It could not stay. Each pass was brief, fast, a narrow window to observe a world no spacecraft had ever seen up close. And what it saw was unexpected. Mercury's surface was covered in impact craters, far more than most planets. The scars of billions of years of collisions, preserved without erosion or weather. The planet looked old, ancient, frozen in time. But then came the surprise. Mariner 10 detected a magnetic field. It was weak, much weaker than Earth's, but it was real. That discovery forced scientists to pause. A magnetic field usually means a moving, conductive interior, a dynamo, something still active beneath the surface. But Mercury is small. Small worlds are expected to cool quickly, to solidify, to fall silent. And yet, Mercury had not. By the end of its mission, Mariner 10 had photographed only about 45% of the planet's surface. Almost all of that came from the same side. Because of Mercury's unusual rotation, the spacecraft saw nearly the same face during each flyby. The rest of the planet remained unseen. Half of Mercury stayed in darkness. Eventually, Mariner 10 ran out of fuel used to control its orientation. Without that control, it could no longer point its instruments or antennas accurately. Contact was lost. The mission ended quietly. What remained was a collection of images, measurements, and questions. We had seen Mercury, but only in fragments. Enough to know it was not simple, not dead, not fully understood. The magnetic field alone was a puzzle that would not go away. It hinted at processes happening deep inside a planet that should have cooled long ago. But there was no way to follow up, no way to stay, no way to watch Mercury change over time. For decades, those unanswered questions lingered. Mariner 10 had knocked on Mercury's door. The planet had answered briefly, and then it fell silent again. To truly understand Mercury, to see the whole world instead of a single face, to listen long enough to hear its deeper story, we would have to do something we had never done before. we would have to stay. After Mariner 10, Mercury waited. For decades, the planet remained mostly unseen, half-mapped, half-understood, and full of unanswered questions. That changed in the early 21st century. In 2004, a spacecraft named Messenger was launched toward the inner solar system. Its journey was slow and deliberate. It looped past Earth, then Venus, then Mercury itself, bleeding off speed step by step, fighting the sun's pull the entire way. 7 years later, in 2011, Messenger finally did what no spacecraft had done before. It stayed. Messenger entered orbit around Mercury and remained there for more than 4 years. Its path was highly elliptical. At its closest approach, it skimmed just 200 kilometers above the surface. At its farthest, it drifted nearly 15,000 kilometers away. This orbit allowed Messenger to see Mercury from every angle, up close and far away, dayside and nightside, equator and poles. For the first time, Mercury became a world we could study continuously. Over the course of its mission, Messenger collected more than 200,000 images. It produced the first complete, global color maps of the planet. It measured chemistry, topography, gravity, and magnetic behavior, not once, but over and over again. Patterns began to emerge. The surface was not uniform, not frozen in a single moment of time. Instead, it was layered with history. Messenger revealed signs that Mercury had shrunk as it cooled. Long cliffs, called scarps, cut across the landscape, formed as the planet's interior slowly contracted. It detected volatile materials where none were expected, substances that should have escaped long ago, yet remained locked in place. The planet's surface told a story of stress and adjustment, of cracking, of compression. This was not the surface of a world that had simply gone quiet and stayed that way. It was a surface shaped by long-term change. In 2015, after exhausting its fuel, Messenger's mission came to an intentional end. With no way to maintain its orbit, the spacecraft was guided into the planet it had studied so closely. Messenger struck Mercury's surface and fell silent. But its work was finished. For the first time, Mercury was no longer a mystery built from brief encounters. It was a world with a detailed record, a planet with evidence etched directly into its surface. What Messenger delivered was not a single discovery. It was context. Enough data to begin rewriting Mercury's history, enough detail to see that this small planet had not simply cooled and stopped. It had evolved. And what Messenger saw, again and again, were marks that told that story, not gentle ones, but scars. Mercury does not forget. Unlike Earth, it has no thick atmosphere, no rain, no wind, no oceans to soften its surface over time. There's nothing here to erase the past. On Earth, impact craters fade quickly. Rain fills them. Wind smooths their edges. Plate tectonics recycle the crust itself. On Mercury, none of that happens. Every impact stays. When an asteroid strikes Mercury, the mark it leaves behind remains almost exactly as it was created. Sharp edges stay sharp. Ejecta patterns freeze in place. Time passes, but the surface remembers. This makes Mercury one of the most heavily cratered planets in the solar system. Its landscape is packed with overlapping scars, layered one on top of another, recording billions of years of collisions. To scientists, this surface is not chaos. It is a record. They read it by looking closely at crater shapes. A crater with crisp, well-defined edges is relatively young. One with rounded rims and softened features is ancient. Its shape worn down not by weather, but by countless smaller impacts over time. By counting craters and comparing their condition, scientists can estimate the age of different regions of Mercury's surface. The denser the craters, the older the terrain. What emerges is a picture of the early solar system as a violent place, a time when debris was everywhere, when young planets were bombarded again and again. Mercury endured all of it. Its small size did not protect it. Its proximity to the sun did not shield it. Instead, Mercury became a target, collecting impacts like a silent witness to the solar system's most chaotic era. In this way, Mercury functions like a fossil record, not of life, but of motion, of collisions, of the restless past of our planetary neighborhood. And yet, as scientists studied the surface more closely, something didn't quite fit. Not every region looked the same. Some areas appeared smoother, less crowded with craters, less worn by time. They stood out. Against a background of extreme age, these patches looked almost younger. That contrast raised a quiet question. If Mercury's surface preserves everything, then why do some places seem to have been rewritten? Why does a planet that remembers every impact also show signs of forgetting? The answer lies not in the number of craters, but in the story of one collision in particular. Because among all the scars on Mercury's surface, one stands apart, larger, deeper, more influential than all the rest combined. One impact, however, stands above all the rest. Among all the scars on Mercury's surface, one stands above the rest. It is called the Caloris Basin. With a diameter of roughly 1,250 kilometers, Caloris is one of the largest impact basins in the entire solar system, so wide that it would span a continent on Earth. From orbit, its structure is unmistakable. A vast circular depression, surrounded by rings of fractured terrain, filled in places with smooth volcanic plains. This was not a simple crater. It was a planetary event. The impact that created Caloris released an enormous amount of energy, enough to reshape the surface far beyond the point of contact. When the object struck Mercury, shock waves raced outward through the crust. But they did not stop there. They continued inward. The energy traveled through the planet's interior, crossing layers of rock and metal, until it reached the opposite side of the world. And there, something strange happened. On the exact opposite side of Mercury from the Caloris Basin, scientists found terrain unlike anything else on the planet. The surface was broken, jumbled, chaotic. Hills leaned at odd angles. The ground looked shattered, as if it had been violently shaken from below. This region became known simply as the weird terrain. It is not the result of a second impact. There is no crater there, no obvious source of force from above. Instead, the explanation lies beneath. As the seismic energy from the Caloris impact traveled through Mercury, the waves converged at the planet's antipode, the point directly opposite the impact site. There, the energy had nowhere left to go. It focused, amplified, and fractured the surface from within. In that moment, Mercury behaved less like a rigid rock and more like a bell struck with overwhelming force. The planet rang. This realization changed how scientists think about impacts. Caloris did not just damage a region. It affected the entire planet. It altered stresses in the crust. It influenced where volcanic material later surfaced. It reshaped Mercury's geological history in ways that extended far beyond its rim. Mercury was not simply hit. It was shaken. And once a planet has been shaken on that scale, its interior cannot remain uninvolved. The Caloris impact did more than leave a scar. It revealed that Mercury responds as a hole, that forces at the surface can reach deep inside. After Caloris, Mercury could never be the same. And as scientists continued to study the data, they began to notice something even more unexpected. Something that did not come from a single impact, but from the planet itself. And then, scientists noticed something even stranger. As MESSENGER continued to map Mercury in detail, scientists began to notice something subtle, but widespread. Long, curving cliffs stretched across the surface. Not isolated features, not small fractures, but massive structures, running for hundreds of kilometers at a time. These features are called lobate scarps. They look like giant wrinkles in the crust, steep slopes where one section of the surface has been pushed up and over another. They are not random. They appear across Mercury's plains, through craters, and over ancient terrain. They cut across features of many different ages, which tells us something important. These scarps formed after much of Mercury's surface was already in place. The cause lies deep below. As Mercury cooled over billions of years, its interior slowly contracted. The core lost heat. The planet's volume decreased, but the crust could not simply shrink smoothly. Instead, it compressed. The surface buckled under the pressure. Rock fractured. Large slabs were forced upward, creating cliffs that still stand today. By measuring the length and distribution of these scarps, scientists can estimate how much Mercury has changed. The numbers are striking. Mercury appears to have shrunk by more than 14 kilometers in diameter since it formed. That is not erosion, not impact damage. That is the entire planet drawing inward. A useful comparison is a drying apple. As it loses heat and moisture, the interior contracts, and the skin wrinkles to accommodate the change. Mercury has done the same, but on a planetary scale. What makes this especially important is timing. Some scarps cut across relatively young surfaces. That means Mercury did not finish shrinking early in its history. The process continued long after major impacts had ended. In other words, Mercury did not cool and freeze all at once. It cooled slowly, relentlessly. Even after the surface looked quiet, the planet beneath was still adjusting, still tightening, still responding to the loss of internal heat. These wrinkles are not signs of violence. They are signs of aging. They tell us that Mercury is not a static world. It is a world still responding to its past, changing shape, one slow movement at a time. And they offer something more, a direct connection between what we see on the surface and what is happening deep inside. To understand why Mercury's crust cracked and folded this way, we cannot stay on the surface any longer. We have to look beneath it. Because Mercury's story is not only written in scars and cliffs, it is written in heat, in motion, in material that once flowed. For a long time, Mercury was thought to be geologically simple, old, dry, inactive. But when MESSENGER mapped the planet in detail, that picture began to change. Large regions of Mercury's surface appeared unusually smooth. They were flatter, less crowded with impact craters, cleaner than the surrounding terrain. These areas became known as smooth plains. On an airless world like Mercury, fewer craters usually mean one thing: the surface is younger. Closer inspection revealed why. These plains were not shaped by impacts. They were formed by lava. Molten rock once flowed across Mercury's surface, spreading outward and filling older craters. It pooled in low regions. It leveled the landscape. For long periods, Mercury behaved not like a frozen relic, but like a planet with an active interior. One capable of melting rock and moving it across vast distances. Some lava flows stretched for hundreds of kilometers. Others flooded entire basins, including parts of the Caloris region. But the most surprising discovery came from features that didn't look like lava flows at all. Scattered across the surface were irregular pits and vents. They had no raised rims, no signs of impact debris. These were explosive volcanic vents. Instead of lava slowly pouring out, these eruptions were driven by pressure. Gases and volatile materials trapped beneath the surface were heated until they violently escaped, blasting rock outward and leaving behind hollowed pits. This kind of volcanism requires something Mercury was not expected to have: volatiles, materials that vaporize easily, substances that should have been stripped away long ago by the sun's heat. And yet, there they were. The evidence suggested that Mercury's interior was richer in volatile elements than scientists had predicted. Not just trace amounts, but enough to fuel explosive eruptions. This forced a quiet reevaluation. A planet so close to the sun was supposed to be depleted, dry, exhausted early in its history. Mercury was none of those things. It had melted, it had erupted, it had reshaped its surface long after its violent beginnings. These smooth plains and volcanic vents told a deeper story, one that impacts alone could not explain. They pointed inward, to heat retained beneath the crust, to materials preserved where they should not exist. Mercury was not just recording external violence, it was expressing internal change. And once scientists accepted that molten rock and volatile gases had played such a major role, one question became unavoidable. If Mercury could melt, if it could erupt, if it could hold onto volatile materials so close to the sun, then what exactly was happening inside this planet? Because the surface was no longer the mystery, the real mystery lay beneath it. Once the surface began to make sense, the focus moved inward. Because Mercury's rocks, its plains, its vents, its scars, were all pointing to the same conclusion. This planet had more heat, more complexity, and more preserved material than it was ever supposed to have. And the reason becomes clearer when you look at what Mercury is made of. Mercury is the smallest rocky planet in the solar system, smaller than Earth, smaller than Venus, even smaller than Mars. But it is unexpectedly dense. Dense enough that for its size, it rivals Earth. That density is not coming from the crust. It is coming from the interior. Mercury is estimated to be roughly 70% metal by mass. Its iron-rich core is enormous, about 85% of the planet's radius. To put that in perspective, Earth's core is closer to 55% of Earth's radius. Earth is rock and water wrapped around a deep center of metal. Mercury is something else. It is almost a metal world with a thin shell of stone, a dense heart with only a relatively small amount of rock left to cover it. And that creates the central question that refuses to go away. Where did the rock go? Because a planet this size should not have been able to keep such a massive core without also holding on to more of its mantle. In most standard models of rocky planet formation, you expect a thicker layer of silicate rock around the metal. Mercury does not match that expectation. And the mismatch is not small, it is structural. This oversized core has consequences. Mercury's surface gravity is lower than Earth's, because the planet itself is smaller. But its interior is powerful in a different way. Rich in metal, capable of conducting heat, and capable of sustaining processes that should have faded long ago. It hints at a history that is not ordinary. a formation story that did not follow the simple rules. Mercury looks ancient on the outside, but inside, it is built like a survivor of something extreme. And once you accept that Mercury's core is far too large to be normal, the rest of the story begins to shift. Because a planet with an interior like this does not simply cool and stop. It changes differently. It reacts differently. It remembers differently. And if the inside of Mercury is unusual, the forces inside it may still be alive. The first hint came quietly. When Mariner 10 flew past Mercury in the mid-1970s, its instruments detected something unexpected. Not a strong signal, not a dramatic one, but a signal that shouldn't have been there at all. Mercury had a magnetic field. At the time, this discovery was difficult to explain. Small planets were expected to cool quickly. Their interiors should solidify. And without motion inside, a magnetic field should fade away. For decades, that question remained unresolved. Then Messenger arrived and stayed. With years of continuous measurements, the picture became clearer. Mercury's magnetic field is real, but it is extremely weak. Only about 1.1% as strong as Earth's. Yet its weakness is not the most surprising feature. Its shape is. Instead of being centered inside the planet, Mercury's magnetic field is shifted. The magnetic dipole is offset northward by nearly 20% of the planet's radius. That asymmetry matters. It tells scientists that whatever is generating this field is not evenly distributed. Something inside Mercury is moving, but not in a simple, balanced way. To understand how, we have to look at the core. A planetary magnetic field is created by a dynamo. Liquid, electrically conductive metal moves inside the planet. As it circulates, it generates magnetic forces that extend outward into space. On Earth, this process is powered by a rapidly rotating planet and a large, molten outer core. Mercury does not have those advantages. It rotates slowly. It has no large moon to stir its interior, and it should have lost much of its internal heat long ago. And yet, the dynamo persists. The leading explanation lies in Mercury's unusual orbit. Because Mercury's path around the Sun is highly elliptical, the gravitational forces acting on the planet change constantly. At perihelion, Mercury is pulled more strongly. At aphelion, that pull weakens. This repeating variation creates subtle tidal stresses inside the planet. Not strong enough to tear it apart, but enough to gently disturb the liquid metal in the core. Over long periods of time, this slow, rhythmic forcing may keep parts of the core moving, just enough to sustain a weak but persistent dynamo. The result is a magnetic field that refuses to disappear. But Mercury's magnetism behaves very differently from Earth's. Its magnetosphere, the region dominated by the planet's magnetic field, is extremely small. It is compressed tightly against the surface by the Sun's intense pressure. Magnetic reconnection events occur frequently. Solar wind particles punch through the field and interact directly with the surface. This interaction is not just theoretical. It helps explain what we see. The magnetic field channels charged particles toward specific regions. It influences how atoms are knocked loose from the surface. It plays a role in shaping Mercury's exosphere and its long sodium tail. In other words, Mercury's magnetic field is weak, but it is active. It is not a fossil remnant. It is not a frozen leftover from the past. It is being generated now. That realization changes Mercury's identity. This is not a planet whose interior has gone completely quiet. Something inside is still moving, still responding, still alive in a subtle, restrained way. as long as the core remains partially liquid, as long as metal continues to circulate. Mercury is not finished. And that raises a deeper question. If Mercury's interior is active enough to sustain a magnetic field under such unfavorable conditions, then its core must have experienced forces far more extreme than we once imagined. Because the present motion hints at something older, something violent, something that reshaped the planet from the inside out. By now, the problem is impossible to ignore. Mercury's core is far too large for a planet its size, which means something fundamental is missing. Rock. Specifically, the mantle, the thick layer of silicate material that should surround a metal core. In a typical rocky planet, the mantle makes up a substantial fraction of the volume. It acts as insulation. It stores heat. It carries much of the planet's geological history. Mercury does not have enough of it. So where did that rock go? The earliest explanation seems straightforward. Mercury is close to the sun. Perhaps intense heat early in its history simply burned the mantle away, vaporizing lighter material and leaving the dense metal behind. For a long time, this idea seemed reasonable, but the evidence does not support it. Messengers showed that Mercury is surprisingly rich in volatile elements, materials that should be the first to disappear under extreme heat. If Mercury had been slowly baked clean by the sun, those volatiles should be gone. They are not. Which means Mercury did not simply lose its mantle by overheating. That brings us to a more dramatic possibility: a giant impact. In the early solar system, collisions were not rare. They were expected. Young planets crossed unstable paths, and massive bodies frequently came too close. In this scenario, Mercury was struck by another large object, not head-on, but at an angle. A glancing collision. Such an impact would have been powerful enough to strip away much of Mercury's outer layers. The rocky mantle and crust could be blasted into space, while the dense metal core, heavier and more compact, remained largely intact. The planet would survive, but it would be fundamentally altered. What remained would be a world dominated by metal, wrapped in a much thinner shell of rock. This hypothesis explains several things at once. It accounts for Mercury's oversized core. It fits with the preserved volatiles, which could have been retained or reacquired later. And it aligns with what we know about the violent nature of the early solar system. But even this may not be the full story. There is another possibility, one that adds a new dimension. Mercury may not have formed where it is today. In the early solar system, planetary orbits were not fixed. Gravitational interactions between growing planets could shift worlds inward or outward over time. Mercury may have formed farther from the sun, where temperatures were lower and rocky material was more stable. Later, interactions with other bodies or the evolving gravitational structure of the solar system could have pushed Mercury inward, placing it into its current extreme orbit. In this view, Mercury's history is not just violent. It is displaced. A planet that formed under one set of conditions, then survived a catastrophic event, and finally settled into a far harsher environment. None of these explanations stands alone as absolute truth. Science does not require certainty where evidence is incomplete. It requires coherence. And what matters is this: Mercury's structure cannot be explained by simple formation models. Its missing mantle tells a story of disruption, survival, and change. This planet is not strange by accident. It is strange because it lived through something extraordinary. And that realization ties everything together. The massive core, the lingering heat, the magnetic field that refuses to die. Mercury is not simple because it is old. It is complex because it endured. But if Mercury lost that much rock, if entire layers of its body were stripped away, then another question follows naturally, one that takes us even deeper. By now, Mercury's story has led us inward, past its battered surface, past its shrinking crust, down toward a core that should not exist in the form we see today. And waiting there is one of the most quietly elegant ideas in planetary science: carbon. Messenger revealed that Mercury is unusually rich in carbon compared to other rocky planets. That fact alone was unexpected. Carbon is volatile. It does not easily survive extreme heat and early chaos, and yet Mercury kept it. To understand why, scientists turned back to Mercury's earliest moments. Shortly after formation, Mercury was likely covered by a global magma ocean, a deep layer of molten rock that wrapped the entire planet. In that molten state, materials began to separate by density. Heavy metals sank inward, lighter silicates floated above, and carbon behaved in a very specific way. It rose. Carbon accumulated near the top of the magma ocean, forming a thick layer of graphite, the same material found in pencil lead. This graphite may still exist today, preserved in Mercury's crust, but that is only the beginning of the story. As Mercury continued to cool, its interior evolved. Layers thickened, pressure increased. Temperatures deep below the surface remained immense. Under those conditions, carbon does not stay graphite. It transforms. Laboratory experiments and computer models show that at pressures of around 7 gigapascals and temperatures near 1,970 degrees Celsius, carbon crystallizes into diamond. Those conditions are not exotic for Mercury's interior. They likely exist hundreds of kilometers below the surface. Based on these models, scientists propose that Mercury may contain a diamond-rich layer, roughly 15 kilometers thick, located at a depth of about 485 kilometers. This is not a scattered deposit. It is not a gemstone vault. It is a structural layer. And its importance has nothing to do with value. It has everything to do with heat. Diamond is one of the most efficient thermal conductors known. Far better than typical rock. Far better than most metals. If Mercury has a deep diamond layer, it would act like a planetary heat conduit, efficiently transferring heat from the core outward into the mantle. That changes everything. A planet with such a structure would cool differently, not rapidly and unevenly, but steadily. Heat would escape at a controlled rate, helping portions of the core remain molten for far longer than expected. This could help explain one of Mercury's greatest contradictions, its magnetic field. A weak field, yes, but one that still exists. If heat continues to flow efficiently from the core, it can sustain slow, persistent motion in liquid metal, just enough to keep the dynamo alive. Not vigorous, not dramatic, but stable. In this view, Mercury's diamonds are not curiosities. They are infrastructure. They do not sparkle. They do not enrich. They quietly move energy. They help explain how a small planet, so close to the sun, with so little mantle, can still generate a magnetic field billions of years after its formation. This idea does not stand alone. It connects. It ties together Mercury's carbon richness, its unusual cooling history, its long-lived dynamo, and its resistance to becoming truly dead. And importantly, it does so without exaggeration. There is no claim of mining, no suggestion of wealth, no fantasy of extraction. The diamonds inside Mercury matter only because they help us understand how planets work. They remind us that value in science is not measured by rarity or shine, but by clarity, by coherence, by how well a single idea can bring many observations into alignment. With this final piece, Mercury's internal puzzle begins to settle. A massive core, a thin mantle, a steady magnetic field, an efficient path for heat. Not random features, but a system. A planet built, perhaps unintentionally, to manage extreme conditions. And in understanding Mercury this way, not as a dead rock, but as a world engineered by chance and survival, we gain something more than insight into a single planet. We gain a framework, because worlds like Mercury are not unique to our solar system. They orbit other stars. They endure other extremes. They survive in ways we are only beginning to recognize. By this point, Mercury no longer feels simple. It has ice, hidden in permanent shadow. It has a magnetic field, weak but alive. It has a long sodium tail, quietly stretching away from the sun. And beneath it all, it has a core far larger than any small rocky planet should. None of these features exist in isolation. Together, they turn Mercury into something more than a subject of curiosity. They turn it into a laboratory. Mercury is the closest rocky planet to a star that we can study directly, not through models, not through distant light curves, but up close. That matters. Because beyond our solar system, rocky planets close to their stars are common. In fact, they may be the most common type of planet in the galaxy. Many orbit so close that their surfaces are exposed to intense radiation. Many experience extreme tidal forces. Many lose atmosphere and material over time. But those worlds are far away. We cannot land on them. We cannot orbit them. We cannot watch them change. Mercury lets us do all of that. Here, in our own solar system, we can observe what happens when a rocky planet lives near a star for billions of years. We can watch star-planet interaction in real time. We see how sunlight strips atoms from the surface, how solar wind reshapes an exosphere, how a magnetic field, even a weak one, redirects energy and loss. We see erosion that does not come from water or wind, but from radiation and particles. We see how material is lost, how some of it escapes forever, and how some of it returns, cycling between surface and space. Mercury shows us that planets do not simply sit in orbit. They respond, they adjust, they survive. What makes Mercury especially valuable is that nothing here is hypothetical. This is not a simulation, not a best guess. It is a real world, shaped by real forces, over real time. When we talk about a planet losing material, we can point to Mercury's sodium tail. When we talk about a magnetic field struggling against stellar pressure, we can measure Mercury's compressed magnetosphere. When we talk about internal heat persisting longer than expected, we can see its effects written into the crust. Mercury becomes a reference point, a baseline, a way to test ideas about planets that we cannot yet touch. In this sense, Mercury is not an outlier. It is a preview, a nearby example of what many distant worlds may be experiencing right now. Rocky exoplanets close to their stars may be losing atmospheres. They may be reshaping their surfaces. They may be holding on to heat in unexpected ways. Mercury helps us understand how those processes unfold, not in theory, but in practice. And it does so quietly. There are no oceans here, no life, no dramatic signs of habitability as we usually define it. But Mercury expands the definition of what it means for a planet to endure. It shows that survival does not always mean comfort. It means adaptation, finding balance in imbalance, stability in extremes. This is why Mercury matters far beyond its size. It teaches us that planets can remain active without looking alive, that internal processes can persist even when surfaces appear ancient, that proximity to a star does not automatically erase complexity. Mercury is a small world with oversized lessons. It reminds us that planetary evolution is not a straight path from hot to cold, from active to dead. It is a negotiation between heat and loss, between structure and stress, between what a planet gives up and what it manages to keep. And because Mercury sits so close, because it allows us to observe these processes directly, it becomes something rare, a place where distant ideas become tangible, a world that helps us understand not just itself, but countless others scattered across the galaxy. We may never visit those faraway planets, but by listening carefully to Mercury, we learn how they might live, how they might change, and how they might survive. And even now, after everything we've learned, Mercury is still teaching, still responding to the sun, still adjusting atom by atom, still revealing how planets endure the most unforgiving environments. And we're not done listening yet. After everything we've learned, one thing becomes clear. Mercury is not finished changing, not finished responding to the sun, and not finished telling its story. Messenger gave us the first sustained look. 4 years in orbit, hundreds of thousands of images, enough data to rewrite what we thought we knew. But it did not see everything. Large portions of Mercury's southern hemisphere remain less detailed than the rest. Some regions were viewed only briefly or at unfavorable angles. And certain processes, especially those that change slowly, require longer observation than a single mission can provide. That is why scientists knew Mercury would need another visit. A longer one, a more patient one. That visit is now underway in the form of Bepi Colombo. Unlike previous missions, Bepi Colombo is not a single spacecraft. It is 2 orbiters traveling together. One is designed to study Mercury's surface and interior. The other focuses on its magnetic field and space environment. This pairing matters. It allows scientists to observe the planet from different perspectives at the same time, to see how processes at the surface connect to forces in space above it. Where Messenger gave us depth, Bepi Colombo adds context. It can observe Mercury's magnetic field over longer periods, watching how it shifts and responds to changes in the solar wind. It can track the sodium tail not as a snapshot, but as a dynamic structure, growing, shrinking, bending, and reforming as Mercury moves along its orbit. It can refine our understanding of the planet's interior, testing ideas about the core, the diamond-rich layers, and the slow flow of heat. None of this promises dramatic surprises. And that is the point. This mission is not about spectacle. It is about listening. Mercury does not shout its changes, it whispers them. Some processes take days to notice, others take years. Some only become clear when patterns repeat again and again. Bepi Colombo is built for that kind of science, for watching the same world from multiple angles, through many cycles of sunlight and shadow. It acknowledges something important about planetary science. Understanding does not always come from discovery alone. It comes from duration, from staying long enough to see what persists and what slowly fades. This is especially true for a planet like Mercury. Its changes are subtle. Its losses are measured in atoms. Its internal motion is restrained, not violent. But over time, those small effects shape everything. Bepi Colombo will not rewrite Mercury's story overnight. Instead, it will add footnotes, clarifications, corrections. It will help us understand not just what Mercury is, but how it continues to be what it is. And that makes it more than a follow-up mission. It is a continuation of a conversation, one that began with brief flybys, then deepened through years of orbit, and now continues with sustained attention. Mercury does not need new myths. It does not need bold promises. It needs time. Time to be observed carefully. Time to reveal patterns. Time to let slow processes become visible. And that is what BP Colombo offers. A chance to listen longer. A chance to hear how a small planet near a star continues to adjust. Not dramatically, not suddenly, but steadily. Mercury will continue to change, even if slowly. And science will continue to follow, step by step, patiently. But for now, there is no need to wait. Because everything we've heard so far, the ice, the scars, the molten plains, the oversized core, the quiet magnetic field, is already enough to shift how we think about this world. Enough to let Mercury speak for itself, and enough to let us rest, knowing that the listening will continue. Just not tonight. It is easy to describe Mercury as harsh, too hot, too cold, too close to the sun, a world of extremes. But that description carries an assumption that Mercury is somehow aggressive, that it is doing something to its environment. It isn't. Mercury does not attack. It does not threaten. It does not act with intention. It simply receives energy. And then it responds. Sunlight arrives. Radiation presses down. Particles strike the surface. Mercury does what any material world would do under those conditions. It absorbs. It releases. It adjusts. Nothing more. In that sense, Mercury is not violent. It is honest. Most planets hide their processes. Atmospheres blur the edges. Oceans soften impacts. Weather erases details. On Earth, change is often disguised. Heat moves slowly. Stress is redistributed. Energy is buffered. Mercury has no such protection. There's almost no atmosphere to filter sunlight. No air to carry heat away gradually. No surface processes to cover what happens underneath. Everything is exposed. When rock expands, it cracks. When heat escapes, it leaves marks. When atoms are stripped away, they form a tail that stretches into space. Nothing is concealed. This does not make Mercury dangerous. It makes it transparent. The same processes that act on other rocky worlds are at work everywhere in the universe. Energy flows in. Matter moves. Structure responds. On most planets, those interactions are softened, spread out, hidden beneath layers of complexity. On Mercury, they are laid bare. That is why Mercury feels extreme, not because it is unique, but because it is less shielded. It is what a rocky planet looks like when nothing stands between it and its star. Seen this way, Mercury becomes less frightening and more instructive. It shows us how planets behave when energy is not moderated, how surfaces respond when time stretches, how interiors cool when heat has a clear path outward. It shows us the rules without decoration, and that clarity brings something unexpected: calm. Because once the processes are visible, they become understandable. Once they are understandable, they stop feeling chaotic. Mercury is not breaking apart. It is not falling into the sun. It is not unraveling. It is doing what it has always done. Very slowly, the planet loses atoms, but it also redistributes energy. It contracts, but it finds new structural balance. Its magnetic field weakens, but it persists. Nothing here is sudden. Nothing is out of control. Mercury reminds us that extremes do not always mean instability. Sometimes they simply mean exposure, a lack of insulation, a lack of disguise. And in that exposure, patterns emerge. The same rules that shape Mercury shape other worlds. They shape rocky planets orbiting distant stars. They shape moons, asteroids, and early planetary systems. Mercury is not an exception to planetary behavior. It is a clear example of it. That is why scientists return to it again and again, not to chase danger, but to understand fundamentals. And for us, as listeners, there is something reassuring in that. Because Mercury's story is not about catastrophe, it is about endurance, about how matter responds to energy over time, about how balance is found even under pressure. Nothing Mercury shows us suggests collapse. It suggests adaptation. The planet is not angry. It is not hostile. It is simply honest about what it experiences. And honesty in science has a quiet power. It strips away fear. It replaces mystery with structure. It turns chaos into process. When we stop seeing Mercury as a hostile world and start seeing it as an unfiltered one, the narrative changes. The sun is not attacking it. Energy is not punishing it. The universe is just doing what it always does. Moving, exchanging, evolving. Mercury lets us see that clearly. And once you see it that way, there is nothing here to rush away from. Nothing to defend against. Only patterns to observe. Rules to understand. Time to let things unfold. That is the shift Mercury invites. From alarm to acceptance. From shock to clarity. From tension to understanding. And understanding brings calm. Because when the universe feels predictable, it feels safe, even at the edge of the sun. And now, with that perspective settled, with the mechanics understood and the fear dissolved, there is nothing left to analyze tonight. The processes will continue without us. The sun will rise and set over Mercury's long days. Atoms will drift away. Heat will move outward, quietly, reliably. And now, we can let the universe keep working. Mercury does not pause. Even now, as this day on Earth slowly comes to an end, that small world near the sun continues exactly as it always has. It turns steadily through long stretches of light and shadow. It loses atoms one by one into space. It conducts heat from its deep interior toward a surface that never truly rests. And beneath it all, a weak magnetic field still holds its shape, quietly deflecting the solar wind. None of this requires attention. None of it needs to be watched. Mercury does not depend on observation to function. Its processes are patient, measured in years, in millions of years, in timescales far longer than a single night. And because of that, there is nothing left for you to do. You do not need to remember the temperatures. You do not need to picture the craters. You do not need to hold on to the numbers or the mechanisms or the explanations. The universe does not ask for that. Mercury will continue to orbit the sun whether it is understood or not. It will continue to respond to light and gravity whether anyone is listening. Its interior will keep cooling, its surface will keep recording time, and its exosphere will keep drifting outward. All of that is already taken care of. For billions of years, planets have done this without witnesses. Stars have burned, worlds have shifted. Energy has moved from one place to another, quietly, reliably. Tonight is no different. The universe is not waiting for insight. It is not waiting for conclusions. It is not waiting for answers. Everything that needs to happen will happen on its own. Mercury does not rush, and neither do you have to. As you rest, that distant world remains exactly where it should be. Neither threatening nor fragile, neither alive nor dead, just continuing. The same is true here. Your breathing will slow without effort. Your thoughts can loosen their grip. There is no unfinished task tied to this story. Understanding can fade now. Curiosity can settle. Awareness can soften. Nothing important will be missed. Mercury's long days will stretch on. Sunrise will take weeks. Shadows will stay cold and still. Atoms will drift away from its surface, guided by sunlight without urgency. And far from all of that, far from the heat, far from the extremes, you are allowed to rest. You are not required to stay alert. You are not required to carry this knowledge forward. You are not required to hold the universe together. It has been doing that long before this moment, and it will continue long after. Tonight, there is no lesson left to learn, no conclusion to reach, no insight that must be preserved, only motion continuing elsewhere. Mercury will keep moving through sunlight. The sun will keep shining. The quiet mechanics of space will remain exactly as they are. And here, now, you can let go. Let the night take over. Let attention fade. Let rest arrive without effort. The universe will stay awake, doing what it has always done. And you can rest without missing a thing. If this journey helped you relax or see the universe a little differently, you're welcome to like the video and subscribe so we can keep exploring quietly together.